In this paper, we delve into the specifics of vision transformers, VIT, large language models, LLMs, vision language models, VLMs, and model compression techniques for LLMs. We discuss the dominance of VIT in visual perception and its upgraded architectural designs such as SWIN, DAT, PVT, and TWINS. We also introduce VLMO, which enhances CLIP with unified multimodality training. We then explore the emergence of LLMs with billions of parameters that are pre-trained on extensive text corpora. We discuss the trend of building smaller language models with around 1B or fewer parameters and the use of publicly available LLMs like GPT-Neo, Pythia, OpenLLaMA, Phi, and Qwen. Next, we discuss the rapid emergence of VLMs and provide a detailed comparison of different VLMs regarding architectures, cross-modality design, and training corpora. We also highlight the preference for clip-fashioned VIT as the visual backbone in VLMs. We then address the challenges posed by the size and computational requirements of LLMs and discuss model compression techniques such as pruning, quantization, knowledge distillation, and low-rank decomposition. We also highlight the development of LLM deployment tools like TensorRT-LLM, LM-Deploy, and Llama.cpp to tackle deployment difficulties. Finally, we emphasize the necessity of systematic and comprehensive evaluations of different VLMs and mention benchmarks like POPE, GQA, ScienceQA, TextVQA, and ME that evaluate different aspects of VLM performance. We also discuss our work related to embodied artificial intelligence and the goal of building egocentric intelligence systems with perception, reasoning, and planning capabilities. In the second part of our paper, we describe the overall architecture of MobileVLM, which includes a visual encoder, a tailored language model, MobileVLM, and an efficient projector, LDP. We discuss the use of pre-trained CLIP VIT L14 as the visual encoder and how Vision Transformer dissects images into patches, applies linear embeddings, and integrates positional encodings. We also discuss the downscaled version of Llama for efficient deployment on edge devices and the use of sentence piece tokenizer and training embeddings from scratch. We highlight the use of rope for positional information and RMS norm for stabilization. We then describe the projector between the visual encoder and the language model and highlight the use of lightweight downsample projector, LDP, based on depth-wise convolution for efficient alignment of multimodal features. In the final part of our paper, we evaluate MobileVLM on natural language benchmarks like SQA, VQA, ME, and MMBench and compare its performance with other open-source models like TinyLLaMA, Galactica, Opt, and Pythia. We also evaluate MobileVLM on benchmarks like GQA, ScienceQA, TextVQA, POPE, and ME and compare its performance with other state-of-the-art multimodal vision language models. We conclude by exploring the use of low-rank adaptation, LoRa, for MobileVLM and evaluate the inference latency of MobileVLM and MobileVLM on mobile devices like Snapdragon 888 and NVIDIA Jetson AGX Orin. We also provide a comparison of the multimodal performance of different model scales, patch sizes, and types of vision language projectors.